So hello together. Today I want to talk about the signal flow graph. It's a graphical representation of the equations of the S parameters, and we have certain graphical elements which we use to represent the S parameter. There at the first point there are nodes. They are used to represent different wave amplitudes AN and BN. So these nodes are graphically represented by dots, and on the other hand we have some branches which are represented by arrows, and they are used to represent the signal flow from a certain node A to a node a node A with the index n to a node A with the index m. And you see here the representation of a very simple equation. So we have here the wave amplitude AN, and here we have the wave amplitude BM, and this wave amplitude BM is given by SNM times AN. So this graphical element, or these small pictures, represents this equation here. So to deal with these graphical elements, we have some basic rules. These basic rules, for example, start with the series rule. So we have, for example, here a wave amplitude AN, a wave amplitude BK, and a wave amplitude BM here. And of course, BK is given by Skn times AN, while BM is given by Smk times Bk. So I can omit the node in the middle by putting these two elements together with a dot in between. So a series element, two series elements go over into a multiplication. On the other hand, we have the so-called parallel rule, and here we have, for example, the element, the dot element, the wave amplitude AN. Here we have the wave amplitude BM, but there are two branches from AN to BM. So this branch we call SMN prime. So there is one way where the signal flows, and we have a second branch which we call SMN double prime. So there is a second way where a certain signal flows from AM to BM. And of course then the two are given by the addition of the both elements. So in total then BM is given by SNM prime plus SN double prime times AN. And in the next step we will discuss a more complicated rule, the so-called loop rule. So I want to talk now about the loop rule, or how we can deal with a loop. We have here the wave elements AN, BK and BN, but here we have a certain loop, a so-called self loop. And how can we solve now for the result between BM and AN? And to do this, we will introduce here a second node which we call BK prime, and BK prime are identical, so we insert here a 1. To solve now for the total S parameter, we start with BM is equal to BM SMK times BK, which is identical to SMK times BK prime. But for BK prime we can say BK prime is given by BK times SKK. This is this term, where these two are identical, and we have skn times an. So we can order this equation into this form. So here we have bk prime times this term is equal to an. So bk prime becomes skn divided now by 1 minus skk, and this can be inserted into this equation, and in the end we find now that the signal the scattering parameter between an and bm is equal to smk times skn divided by 1 minus skk. So of course there may exist more complicated signal flow graph, and if there are more complicated signal flow graph, I want to give you the hint to have a look to the rules of Mason. So we go on now considering the signal flow graph, and as an example I want to introduce here the signal flow graph for one port. Of course, if I have a one port, it's quite easy. We have the wave amplitude A1, B1, and it's connected via the S parameter S11. A little bit more complicated is if we have a two port. Of course, then the two port is described by its S matrix, and we have here A1, B1, B2, A2, and here are the parameters. So B2 becomes A1 times S11 plus S22 times A2, or B1 becomes S11 times A1 plus S12 times A2. So, and then as an application or as an example, I want to study now an amplifier which is terminated in a certain load reflection coefficient. So I assume our amplifier is here, and it's given by its S parameters, and this amplifier is terminated in a certain load reflection coefficient. So we have here then the signal flow graph of the whole situation, and the question is now what will be the input reflection coefficient we will see into our amplifier. And to start, if I want to calculate the input reflection coefficient, I have to calculate B1 over A1. So we can start with the equation B1 is S11 times A1 plus S12 times A2. So these are the two components which result in B1. But the problem is now this loop again. So we have a look to the wave amplitude A2, and A2 is given first, in the first step, just by RL times B2. But B2 again is composed out of two out of two branches. So one branch is given over A1. So we have here, if I have a look to A2, then we have, this is B2 times RL, but we have this times A1, so this gives the first term. And the second term is given now by RL times S22. So here again we have A2 and A2, and so we can resolve for A2 and end up in this expression in independence of A1. Of course, this we can insert here, and if I now solve for order in for A1, then we come to this expression, and the final result for the input reflection coefficient is given by this expression. And one point which is very important here, we see, oh, here our L is missing, I see. Our L is missing here. But a very important point here is now that if the influence of port 2 to port 1 would vanish, so if this would be 0, then of course the input reflection coefficient would be given only by the S parameter S11 of the transistor. But since normally this element is quite small, but it still exists, then the output reflection coefficient will also have an influence on the input. And the problem is, of course, this denominator here, because in certain situation, of course, this denominator can become 0, and this will find to result in instabilities, which we will see later in our lecture.